Welcome back, everybody. Please grab a seat. Today there is seats available for everyone, which is awesome. And then I think we're about ready to hear about embedded toolchains using LLVM. Please give a warm welcome to Peter Smith.
Yeah, hello everyone. My name's Peter. I'm an engineer in ARM's compiler team. I'm mostly sort of focused on the embedded side because there's sort of several compiler teams within ARM. But today I'm here to talk about how to use an LLVM toolchain via open source. Okay, so first, this presentation was actually given at FOSDEM or kind of variant of that. So if you happen to be at FOSDEM, there's a lot of this will be actually be very familiar if you went to the LLVM toolchain. So what I've done for this one is kind of the bits where in the LLVM development room I can make some assumptions of what people know about LLVM here. You obviously know about the embedded system side, whereas at the LLVM dev room that wouldn't be as common. So this bit is just a little bit about what makes an LLVM tool, an embedded toolchain different from a hosted toolchain, because Clang and LLVM has very much come out of the hosted sort of toolchain, and it's sort of, I guess, only relatively late in its lifespan has been adapted to be used as an embedded toolchain. So typically when you have a sort of hosted toolchain, this is when you're, say, just programming in Linux natively, whatever, you just use Clang or GCC at that particular point. So it's actually relying on the underlying operating system to provide a lot of these sort of features for the library, so you can kind of build your, say, C library on top of the operating system primitives, that type of thing. And typically there'll be a linker and assembler already there, and your libraries will be, you know, part of the system libraries or the platform libraries at this particular point. And if you're, say, targeting Linux, you're targeting a platform, you're not necessarily targeting a very specific set of hardware. So, for example, if you're targeting ART64 Linux, you might actually be targeting just the base variant of that and none of the additional sort of hardware features. So typical embedded toolchain that you might be more used to. So that particular embedded toolchain can't make any assumption of what operating system you're using, real-time operating system. It was brought up this morning in the RTOS talk that there's a little bit of an overlap about what the operating system will provide and what the actual toolchain will provide. There is actually a definition, a freestanding definition in C++ that says this is the minimum that you need to provide, although it doesn't necessarily have a maximum at that particular point. So you'll find that the C libraries for an embedded toolchain will actually include a bit more than what will be in the C standard to enable things to go for there. And one of the advantages that you do have as an embedded system is that you can typically target precisely the hardware that you're going for and not a platform of some sort. Also, I suppose as a tool chain, you'll find that there's lots and lots of different library variants that you have to supply with. From some of you might be using at the very smallest level microcontrollers, some might be using a much more performant one, and there'll be different libraries for each particular one. And obviously, you can't run Clang on a Cortex M0, so you have to use some form of cross-compilation at that particular point. Okay, so that's all with that there. So the next thing is just a motivating factor. Why do we actually want to use LLVM in embedded context? So I'm assuming here that most of you who are using an open source toolchain will be familiar with the GCC embedded toolchains, and that's where I expect most of you will be coming from at this point. So the ones that I'm most familiar is the ARM LLVM, the ARM embedded toolchain in this particular bit. So there are some advantages of using LLVM at this particular point. So one of them is the amount of runtime configuration that you have with Clang. So with GCC, you typically have to, when you are actually building GCC, a lot of the sort of configuration parameters are baked in when you build that compiler. So you don't, with a single GCC executable, you can't say target Intel, ARM, and ART64 within the same binary. So this is actually, I suppose you could say, not really that important if you've only got one target bit of hardware, but if you're, say, a company, and particularly with something like adaptive AutoSAR, and you're looking for a compiler that might have to target multiple devices and it might need to be safety certified, then having one tool chain that you can safety certify for multiple different targets is quite valuable, as opposed to having multiple tool chains that you might need to certify independently. Certainly in terms of code generation, sometimes GCC is more mature for particular targets, and sometimes Clang. Just it all depends on which of these the actual developers implement these features first. So the new Cortex M85, which has something called an MVE, which is sort of a effectively a SIMD unit for microcontrollers, that type of thing. That's was developed first for LLVM, so the code generation for that is currently better in LLVM for that particular point. Next thing that you see, you can take advantage at least of some of the sanitizers. I know security has been a big topic yesterday. So there are some of the things you can do even in an embedded context without runtime, and I'll come into that into a little bit more detail later on. Obviously, if you're familiar with Clang, then using it is quite nice. And the other thing that you've got is diversity of implementation. So obviously, the more compilers you can use to compile your software, the more bugs that you're likely to find in it. Okay. So here's my little aside on using sanitizers in embedded systems. So I'm making assumptions that you're aware of these, but just in case you're not, you've got things like UBSAN, which is the undefined behavior sanitizer. That's where the compiler will insert runtime checks for certain forms of undefined behavior. Local bounds sanitizer is kind of a variant of UBSAN, but that can catch a few more things, like because it's inserted at the back end rather than the front end of the compiler. You can actually use the control flow integrity sanitizer. It does have the disadvantages that you need link time optimization, which again can be somewhat problematic with embedded systems. Again, I've got a bit of a slide on that later. There is actually a relatively new sanitizer, the kernel control flow integrity sanitizer, which has a very unfortunate acronym of KCFI, and I keep on saying KFCI, whatever at that particular point. At least I didn't write it wrongly in the slides this time at that point. And that's actually a lower overhead one that you can take advantage without needing link time optimization. So just to show how you can use the undefined behavior sanitizer. So by default, it will call out to a runtime function, which typically you won't get supplied with your toolchain. But if you can tell the compiler to use it in traps only mode, where essentially it'll, well, basically halt the program if it detects undefined behavior, you just need to add fsanitize-trap, and then there's all sorts of configuration options where you can choose which one to go for. So as an example here, this is just a very simple bit of C code that can have undefined behavior if there's an overflow. Then there's this just shows the actual code that will get inserted. So for example, it's just doing a comparison. If it detects overflow, it just basically halts the processor by executing an undefined instruction, that type of thing. Now, there is actually something called the minimal runtime, where instead of actually calling, instead of halting, it will just call a known UBSAN runtime function. And with a minimal runtime, you can implement this yourself fairly trivially. You might have it say, write to a serial console or something like that and say, hey, this undefined behavior happened, continue, that type of thing. But the main message I'd like to take away from that is that you can actually use some forms of undefined behavior sanitizer fairly simply and without any extra library requirements, and the overhead is fairly low. Okay. Stepping up in complexity is the control flow integrity sanitizer. So control flow integrity was mentioned yesterday. So what the compiler does in this particular case is for every function pointer, it basically makes a signature from the type signature. So there I've got a function pointer that's just a void function returning an int, and that has a particular signature of that .long that's there at the top. And what the control flow integrity sanitizer does before calling an indirect function is it basically looks at the address 4 bytes above where the function address is supposed to be and checks that the signature matches. So just, you could say, it means that if you were an attacker and you've managed to take control of the stack, wouldn't necessarily be in the stack in this one, this would probably be in controlling the variable that you're about to jump to, then they can only jump to places of the same signature at that particular point. So it's not perfect, but it is something that's fairly low cost to be able to do that. The obvious disadvantage of doing it in this particular method is that pretty much you actually need to have the code that you're calling the function pointer of to be compiled with the signature, because if that signature is missing, it won't work. So say, for example, if you've got library code that isn't compiled with KCFI, then you'll need to write a wrapper around that. Otherwise, then you know, if you say take the address of memcopy, then that won't have the signature at that particular point. Okay. So the one that everybody, I guess, would like to use but can't, and this is, I guess, probably a justification of why you can't currently do this, is ASAN and MSAN. So these are sort of things that you can use on mostly platforms with virtual memory. And what these sanitizers do is kind of the equivalent of what Valgrind does, and can sort of, I think ASAN is where it can sort of trap out of bounds writes, and MSAN is for trapping use after free. What they use is this concept of shadow memory, which is basically memory that has metadata about what bytes are in use, that type of thing. And then there's a kind of compile time mapping from the shadow memory to your normal memory. And then it kind of, when you do operations like malloc, whatever, then the version of malloc has to be customized to basically write to the shadow memory to say what's used. And then essentially, there's quite a high runtime overhead for this. So at the moment, the sanitizers require dynamic linking because they kind of intercept things like malloc, free, memcopy, that type of thing. And they also, you know, rely on other sort of bits of the sort of, I guess you could call a POSIX environment to implement the sanitizer runtime. Now, it is in theory possible to write this from embedded systems. So in the Linux kernel, there's a sanitizer called KSAN, which I think I've unfortunately written as KSAN there. Sorry about that. So that's, I mean, the Linux kernel is essentially a giant embedded system at this particular point, but it does have its own, I mean, essentially what they've done is they've done all of the work for the underlying memory management primitives in the Linux kernel to basically make them sanitizer aware. At that point. So the reason this is very difficult for, say, an embedded toolchain to provide sort of out of the box is that everyone's embedded system is different. They all use different memory allocations and that type of thing. So it's just very, very difficult to make this out of the box. It also at the moment relies on virtual memory. I mean, in theory, you could do this without virtual memory, but again, you then have the problem of how do you map, you know, for your particular embedded system to what memory is available, that type of thing. Anyway. So moving on a bit, this is just some of the moving back to the sort of LLVM sort of part of the toolchain. So for those of you that don't know, the LLVM project is hosted at GitHub in LLVM project. So it used to be several independent repos in Subversion. Now it's one giant mono repo where you've got Clang, you've got the linker LLD, you've got the sort of code generator itself, LLVM, the runtime library, compiler RT, libc++, the C library, that type of thing. So you've got pretty much all the components you need for a whole toolchain in that one directory there. The one bit we're missing at the moment is a C library. So there is a project called LLVM libc that is starting up. It's currently not complete. And I'd say currently it's mostly focusing on, I guess you could say, platform and optimizing performance rather than, say, necessarily code size. But that is something that I think that the authors of LLVM libc would like to address with, say, multiple embedded systems here. So technically, GCC doesn't have a C library either, but it does at least have in its configuration files how to interface with newlib at this particular point. Okay. So how would I actually build an LLVM toolchain? And it's actually not very easy at that particular point. Now, building the tools is actually very easy. Because they all cross-compile natively. It's almost as simple as going, cloning LLVM repo and just using CMake, then Ninja or Make, and there's basically all of your cross-compilation tools there. Unfortunately, the runtime libraries, you need to cross-compile those separately. And if you've got, say, if you're building a toolchain for multiple different architectures, you've got to build those library variants multiple times at that particular point. So ARM does have an open source recipe for building an LLVM toolchain. So this is, I say, our first attempt at making an LLVM equivalent of the GNU embedded toolchain. So essentially, it's a set at the moment. It's a set of build scripts. So we're using picolibc for our C library rather than ulib at the moment. And at the moment, we're focused on Cortex-M, although we do have some experimental support for A profile with AOUT64. So in principle, there's nothing really ARM-shaped about this particular tool chain. It's just that we've set the various configuration options for build for ARM. So it's certainly something that you could adapt for anything that, any target that both picolibc and LLVM support. Yeah, there are some binary releases available. We can make those available for Linux and Windows using MinGW at the moment. But yeah, so that's sort of basically something that at the moment is sort of a public service announcement. Hey, we're looking at people to try this out. It's very early days at the moment, and there's going to be a long road to keep improving it over time. Hopefully, working with the upstream LLVM community to get more features involved there. Okay, so what's the usability of an LLVM-based toolchain compared to, say, the GNU Toolchain? So one of the principal things that's missing at the moment is multilib support. So multilib support is, when you say I'm targeting a v6m, you want the v6m libraries, and you don't really want to have to write out the path to the v6m libraries in your toolchain. You want the toolchain to do that for you, and that's what multilib does. So far, there's hard-coded support for multilib available in Clang right now, but there's not really a data-driven version that sort of would allow an embedded toolchain manufacturer to sort of easily make their own multilibs up. So we have some patches up for review there. I'll mention those later on. Another thing that's missing is something called specs files, which are kind of like fragments of command line configuration. I'll go into those in a little bit more detail later. So in the GNU toolchain, you can choose between, say, newlib or newlib nano by just basically using these specs files, that type of thing. So Clang's got something called config files that are similar, but they're not quite as general. So you'll find with the LLVM embedded toolchain for ARM, we've basically, you could say, emulated multilib and specs files with the config files, but it's meant that we've had to have a lot of config files for lots of different ones, because we're basically just making one config file for every possible combination, which isn't particularly scalable at the moment. And what we're also expecting is a long tail of small incompatibilities. So whilst the GNU assembler and the LLVM integrated assembler accept the same syntax, there's bound to be small incompatibilities between the two. There might be some feature that GCC supports that Clang doesn't, and vice versa, that type of thing. Okay. So it's a quick example of what I meant by multilib. So yeah, it's just, as you can say, for say v6m, v8m, and ARM, thumb, all of the various different forms of floating point, whether you have no floating point or a hardware floating point library. You basically have to duplicate each of your libraries for each of this particular case, duplicate your startup code, and ideally you want your toolchain to just basically select all of that directories for you at that particular point. Specs files, again, just going to go through this really quickly because it's not particularly interested unless you're really into toolchains at this particular point. But yeah, specs is kind of like an internal language for GCC configuration, and you can overwrite it with the specs files. And that's one of the ways that essentially the GNU ARM embedded toolchain chooses between newlib and newlib nano, is essentially it renames the library from -lc to -lc_nano, that type of thing. I mean, in theory, you could do that with multilib, but then you'd need to invent more command line options to be able to do that. So here's the Clang equivalent. It's a config file. So I'm just basically here quoting one of the config files from the ARM embedded toolchain. So yes, effectively what we're doing there, selecting the target. That's the ARM v7em-none-eabi. Selecting what sort of floating point calling standard we want. Selecting the floating point unit. Selecting the linker. We don't want exceptions or RTTI. That CFG-dir is basically just a way of accessing libraries relative to the Clang executable, which means that you can move the toolchain around without breaking everything. Okay. Final slide that I've got here, just a little bit about link time optimization, because this is something that I mentioned earlier on. that link time optimization can be a pain for something like CFI. So certainly, if any of you are able to use link time optimization, it certainly can get you quite a bit of performance and code size benefits. It's particularly aggressive at removing unused code at that particular point, although, to some degree it can be a bit too aggressive in that it can take out, bits of code like the vector table that you think, I don't really want it to take that out, so you have to sort of make sure that it keeps it at this particular point. But essentially what's actually happening at link time optimization is the linkers actually doesn't actually have that much to do. It's essentially all it has to do is take in the bitcode files, which is the LLVM sort of intermediate representation, and instead of trying to link them, it just extracts the symbol information from them, combines that with the symbol information that it gets from the normal ELF file, and then it gives all that information to the LTO code generator, and then that will then spit out a single ELF file that with a sort of, with a very strange name like /tumps/LLVM_LTO.o, and that ELF file then just gets processed as if it were any other ELF file by the linker. So almost all the hard work there has been done by the LTO code generator. Okay. So some of the problems that you can get with LTO, particularly with link scripts. So if you'll generally find that you'll get one great big object file back with all of your with basically all of the functions in .text, and LTO at the moment is blissfully unaware of any partitions that you might have had with your linker script, like saying, I really don't want things in my flash getting inlined into ROM and vice versa, that type of thing. There are some cases where you might not have all of your sections in memory at once, and if LTO will assume that it can access data from both of them at the same time, it can cause problems. So essentially, the summary that I to give you here is that LTO is not output section aware. It has no idea of different memory speeds or the sort of things that you want to do. But if you can fit your application into a single .text file, linker script, and you can basically live with the restrictions that LTO provides, it certainly comes highly recommended for code size and performance. Sadly, it does tend to muck up the debug illusion somewhat, particularly at higher optimization levels, but that's probably the same of 03 at most cases. Okay, so I'm probably going to skip through these fairly quickly because this is mostly from the LLVM code generation, more compiler internals than you probably want to care about right now. But if you are interested in how Clang does this, in essentially every target, it breaks down into this architecture, vendor, operating system environment, that type of thing. And Clang basically matches that to a toolchain class that you can go and look up what toolchain class there are. So there'll be, for example, a Linux toolchain class. Then that might get specialized for Android. And there's essentially, for us, we use the bare metal driver for this particular bit. So this is sort of just showing you the mapping that you might get. So ARM Linux GNU might go to Linux, x86-64 unknown might fall back to generic GCC driver, that type of thing. So almost all of the logic here is going to go into the bare metal driver. So that bare metal driver that we're using, it defaults to LLD, the LLVM linker. It defaults to the LLVM runtimes. So yeah, that's compiler RT, which is kind of like the equivalent of libgcc, if you're aware of the GCC runtimes. It uses LLVM, libc++, and exception unwinding, that type of thing. Always uses Clang integrated assembly. You don't have a separate assembly like you do in the GNU Toolchain. And it does rely on the user to have the right include and library path at the moment, although that's something that we're hoping to change with multilib support. Okay. So one thing I also just finally wanted to mention here for any of you doing embedded Linux work and maybe aren't aware of this is that Clang can actually now build the Linux kernel. That sort of all of that works come from the Clang built Linux project. So there's some sort of useful scripts to help build and test a kernel for that particular bit. So you can get the instructions available in the kernel build system. Just look for this. Just basically look for the Clang sidebar on that particular part. And as the Linux kernel has minimal to no requirements on the runtime library, you don't need a C library in this particular case. It's simply just a case of selecting the right target, and it'll it'll build. And Yocto, which for those of you who are not familiar, is a kind of, I guess, a project for sort of building your own embedded Linux distribution, has some support for Clang via the sort of meta Clang which is, I think, sort of a toolchain recipe for building that. Okay, so here's just a final little bit about some of the ongoing work we're doing in this area, and essentially how to get involved if you are interested in that. So we are working on the data-driven multilib support. So there is there's an RFC out on the LLVM. Well, I would have said the mailing lists, but the mailing lists have moved to something called Discourse. So if you are interested at all in the LLVM community, discourse.llvm.org, that type of thing. So uses a different mechanism than GCC, but yeah, that's something that we're hoping to land fairly soon, and that will go into upstream LLVM, hopefully within a matter of a month or two. So future work, there's a project out of Texas Instruments to make link time optimization more usable with linker scripts. That's essentially making them output section aware. As an attempt at improving code coverage as well. So again, talk from Texas Instruments. There's some patches out there for MCDC code coverage, which is probably not necessarily interesting for you unless you're in through for functional safety certification, but certainly MCDC code coverage is required for higher levels of certification, that type of thing. Yeah, and then there's LLVM libc, so it's focused on the hosted use case for now, but expected to improve in the future. Some very, very quick plugs for ARM, I guess, at that particular point is, I don't know if anyone actually uses Big Endian at all for ARM. I don't know. It's one of ARM is still, I guess you could say, very heavily biased towards Little Endian stuff, but Big Endian does exist, and we'd like to add support to that for LLD. And for anyone who's working in the security industry in terms of building a secure extensions that's using CMSE or TrustZone M, then we're adding support to LLD there as well. Okay. So yeah, this is the message for the LLVM dev room, but it's also useful to mention here. There is a LLVM embedded toolchains working sync up. It's Thursday, which I guess it would be 6 o'clock in German time. It's a bit unfortunate, but essentially it's how do you pick a time slot that works for both the US and Europe at the same time. And yeah, the best way of doing that is just looking for the LLVM community. We've got an agenda and meeting notes there, and that's not just for people who want to contribute to the toolchain. Anyone who just wants to sit in, listen, or say, hey, this would be really useful for me in my project, that type of thing. Discourse as well for questions. For bug reports, basically problems in LLVM, report them to LLVM. We do have in the LLVM embedded toolchain for ARM an issues list, although if you do find a bug in LLVM, please don't report it in the LLVM embedded toolchain. We're kind of more the build scripts. We'd much rather get the bug reported in the upstream project at that point. Also, roundtables available at LLVM development meetings. I think that's all I've got for now. So hopefully we've got about 10 minutes. If anyone has any questions on LLVM, Clang, anything like this in general, I'll do my best to answer.
Hello, thank you for the talk. I've got a question particular to the commercial Clang compiler from ARM.
Yeah.
What is the relation between that and the LLVM toolchain, and what is the future for it looking like?
Right. Okay. So in the ARM commercial toolchain, this is ARM compiler 6. Essentially, I'm just going to deviate into merge strategies at the moment, but basically LLVM, the open source project, has like hundreds of commits per day. If you have a commercial compiler or anything like that, you've basically got to figure out how to do a merge, and you either do a merge, pretty much continuously merge and stay at tip of trunk, or you kind of back over. So we follow the tip of trunk merge strategy. So essentially ARM Clang, which is what we call the compiler in ARM compiler 6, is Clang. Pretty much will be the, when ARM Clang is released, it'll be equivalent to the LLVM release that was most recent. So, for example, the next release of Clang will probably be based on Clang LLVM 16, that type of thing. And essentially, the ARM Compiler 6 has a proprietary linker and libraries and assembly, and basically all of the, I guess you could say, the evolution from ARM Compiler 5. So most of the changes in there are essentially how to handle those proprietary components. But also in there is support for new IP that ARM have just released that hasn't yet made it into upstream. So we do try and upstream the new IP support as quickly as possible. Typically for an end user, it's not that important because by the time that ARM's released the design, it's like 2 years before anyone's built the chips anyway. So by that time, it would end up in open source. So yeah, that's kind of the relationship between the two.
Any other questions, comments?
I assume there wouldn't be any problem if I want still to use the binutils linker.
No, there's no problem. Essentially, if you there's an fuse-ld option, and you just point it at BFD, and it would work. Yeah.
Any other question? If not, I think you'll be around for tonight's party, and you can deep dive into discussions that are just too long for this kind of format. Thanks again, Peter, for the talk.
Okay.